it will be presented by Henrique Fingler, a CS PhD student from UT Austin. And his research interests include virtualization, acceleration, virtualization, and systems for machine learning. And Henrique will tell us about Lake, a system that exposes accelerators to kernel space for supporting machine learning-driven decision-making.
Hi, my name is Henrique, and I'll present our paper towards a machine learning assisted kernel with Lake. This is joint work with my colleagues Isha Tarte, Hangchen, Ariel Szekely, Bodun, Aditya Akella, and Rossbach. This is a talk about machine learning in operating systems, more specifically machine learning-based resource management. I'll first discuss why we should use ML in the OS. Then I'll talk about the goal of our work, discuss the implications of ML in the design of OSs, and how to best support ML in the OS. I'll then show the evaluation of an ML-based kernel application. There's a delicate balance between the rate of hardware evolution and the heuristics in the OS to manage those resources. OS heuristics must keep up with the ever-increasing rate of change in the underlying hardware and software. As new features are introduced, heuristics must adapt. Hand-tuning these heuristics and maintaining correctness as the underlying system and the objective function changes is an effortful process that can become impractical. Complex hardware has been continuously designed and pushed into systems. Servers now have numerous cores and significant application diversity. We believe that ML can help the OS deal with this complexity. We conjectured that the adaptivity of machine learning can better explore the solution spaces that are currently handled by heuristics. Others have made the same conjecture and study replacing individual subsystems in the OS with ML, often without end-to-end OS integration. Unlike those works, the goal of ours is not to prove the utility of ML for a particular OS component. Instead, we focus on the fundamental questions and the design implications of ML integration in the OS. So integrating ML in the OS will raise many challenges. For example, machine learning algorithms can be computationally expensive. Subsystems that rely on ML may be latency critical, requiring fast inference. ML subsystems will need to take care not to contend for resources with user applications or harm overall performance. Another challenge is capturing and managing feature vectors to train and perform inference. A feature vector is a collection of measurements of observed system state that forms the input to ML inference or training. Adding code to the kernel to allocate and capturing features is a nuanced endeavor that is even more difficult when we compose multiple ML-based subsystems. For example, locking disciplines must be followed. If capturing a feature requires interrogating data structures from different subsystems, locks can be required, and locking across module binaries can violate locking disciplines and cause deadlocks. To address these challenges, we built Lake. To address computational demand, Lake enables hardware acceleration in the kernel. To better manage accelerators, Lake allows developers to write custom policies to control contention and variable profitability. To facilitate feature management, Lake proposes a lock-free in-kernel feature registry. We believe hardware accelerators will be key to support ML in the OS because, for example, accelerators can take pressure off CPUs and lower inference time. Unfortunately, accelerator libraries are inaccessible from kernel space. They are designed for user space and cannot be used by the kernel directly because such libraries may use mechanisms or context that is not present in the kernel. For example, accelerator libraries typically use kernel bypass techniques to communicate with the accelerator. Their I/O control functions are opaque, and interacting directly with the accelerator may require proprietary context information. Lake extends the AVA
project from ASPLOS'23 to support accelerators in the kernel through upcall-based API remoting. We focus on the CUDA API and TensorFlow, but Lake can be extended to support other accelerators and libraries. The Lake kernel module exports function symbols that match the accelerator's library. When one of these functions is invoked by the kernel, Lake upcalls a user space daemon with what API was called. The user space executes the API, which then reaches the accelerator. Communication between kernel and accelerator is optimized by using low latency upcalls and zero copy mechanisms. We identified two problems when we support accelerators for ML in the OS. First, GPUs are only profitable when a certain amount of data is processed at once. I'll discuss this issue in the coming slides. Second, we cannot contend for resources, such as the GPU, with user space applications. This figure shows the throughput of a GPU accelerator user space applications with and without kernel space contention for GPU resources. At T0, the user space application starts using the GPU. At T1, an ML-based page warmth classifier in the kernel starts using the GPU. At T2, an ML-based I/O latency classifier in the kernel starts using the GPU as well. The user space application sees a performance drop of up to 68%. Lake provides a framework to manage this kind of contention by transparently modulating which compute resources are used based on policies expressed in eBPF. Initially, the GPU is idle, so the kernel can use it. When the user application starts using the GPU, the kernel subsystem has to back off the GPU to not harm the user application performance. When the user application completes, the OS can use the GPU again. In the previous slide, I told you that Lake uses eBPF to express policy. In this slide, I'm showing an eBPF fragment that illustrates how Lake can enable policies to manage contention and variable profitability. I don't expect you to read the entire code. I'll just guide you through the relevant parts. So Lake enables custom policies through eBPF because it enables dynamic updates and strong safety guarantees. In this example, which is called right before inference, we can manage contention by polling the GPU utilization, and based on the utilization, we choose to use the GPU or not. Additionally, for a variable profitability, we can get the current batch size, which is the number of inputs we have accumulated so far to perform inference. And in case the batch size is greater than a certain threshold, we use the GPU. One problem that we have not talked about is what if an ML model starts behaving badly? So a pathological series of decisions may severely harm the system performance. This policy mechanism can provide guardrails to ML, helping the system maintain solution qualities within thresholds. We can modulate execution based on solution quality, which includes falling back to the original heuristic. On this slide, I'll illustrate why Lake needs explicit in-kernel support for feature management. Suppose we want to collect two features in the block I/O subsystem, how long each I/O took and their size. We need to add a feature vector data structure and implement functions to allocate and manage them. We need to insert code at the point where an I/O is issued and allocate a new feature vector. Then record the timestamp and the size. When the I/O is complete, we store the timestamp difference. When these custom feature capture routines read data from a kernel subsystem, we need to make sure that they follow locking disciplines. If one acquires a spin lock that was already acquired, or if it sleeps while holding a spin lock, it can deadlock. Spin locks have variants that can enable or disable interrupts. If you use the wrong one at the wrong time, you can damage the kernel behavior. Lake solves this problem with a lock-free in-kernel feature registry and an asynchronous API to simplify schema definition and instrumentation of the kernel to collect feature data. The API uses a transaction-like interface
that enables the developer to begin a phase of feature capture, capture individual features, and end the capture phase, all at arbitrary different points in the kernel. In this example, with Lake's feature registry, no additional data structures are necessary because a schema is created beforehand that allows Lake to manage data structures transparently. We call an API that creates a new feature vector and capture the I/O size and timestamp. When the I/O ends, we capture the elapsed time and commit this feature vector. Our paper presents the entire API of the registry and an extended case study. Now to evaluation. Our paper presents 6 workloads. In this presentation, I'll focus on the I/O scheduling workload based on LinOS, which was the focus of a paper from OSDI 2020. The setup for this application is a server with 3 NVMEs with data replication. This application classifies the latency of an I/O as fast or slow. In case the I/O is predicted slow, the I/O is rejected and reissued to a different device, assuming that it will be faster. The original neural network is small, so to evaluate Lake's ability to support more complex models, we enlarge this neural network by adding 1 or 2 layers to the neural network. These are represented by the +1 and +2 suffixes. More details on these models and evaluation can be found in our paper. The graph on the right shows the time taken to perform inference, the y-axis, on variable batch sizes, which is the x-axis. We do this experiment to find if using a GPU is beneficial and at what point. We call the point in which a GPU starts performing better than the CPU the crossover point. We are interested in crossover points since once we discover them empirically, we can use them to set policies for when to use a GPU. In the original neural network, using a GPU is only profitable with a batch size of 8 or more. For larger models, the crossover point is at just 2 inputs. So as expected, as the batch size and model complexity increases, using a GPU becomes profitable faster. We also perform an end-to-end implementation of this I/O scheduling subsystem. We run synthetic workloads with different I/O properties, which are shown in the table, on the 3 NVMe devices in the server. The y-axis is the average end-to-end time of an I/O request, and the x-axis are the workloads. We develop a simple policy that chooses when to use a GPU or a CPU using the calculated crossover point and the burstiness of incoming I/Os. This is represented in the graph by the solid bars. Always using a CPU is represented by the slashed bars. Due to lack of time, I'll not discuss the baseline, and we only focus on 2 workloads, Azure and Bing I. I'll be happy to talk about the others offline. Workloads with many IOPS, like the Azure workload, allows the accumulation of many I/O requests into larger batches, so using a GPU is more profitable. For the original neural network, using a GPU is not profitable since the model is very simple. As model complexity increases, which are the 4 rightmost bars, the GPU significantly lowers I/O latency due to the inference time on CPU versus GPU. As IOPS decreases, so does GPU profitability, even with more complex models. In this case, the CPU is the better alternative, which can be observed in this Bing I/O workload. This shows the necessity of adaptive modulation policies to use hardware acceleration efficiently. There is more evaluation in our paper, including 5 other workloads. In conclusion, we believe ML will eventually be used by OSs to manage resources, which means we need shared infrastructure, frameworks, accelerator accessibility, and ways to manage variable profitability and contention. To address these issues, we introduced Lake. Thank you, and I'm open to questions.